Okay, um, so this class I'm going to cover about some of the work that we are currently doing, and like tomorrow, I will cover about like what are still some of the controversies that exist, some of the limitations of resting state, and perhaps like what could be future work. Okay, so there are like this would be like three areas that we have been working for the last few years. And one is understanding the relationship between physiological and neuronal fluctuations at high frequency, right? As we have discussed, the fMRI signal has low temporal resolution, and with fMRI we get data typically once every 2 seconds, right? So if we get data once every 2 seconds, then our Nyquist bandwidth is going to be only 0.25 hertz, right? So in 0.25 hertz, we can only see, the low frequency fluctuation and the respiration signal. All other signal are going to be, aliased. So how can we process the data? What could we do? Also, thank you so much. The second is about dynamic connectivity. Um, like yesterday and day before, I have tried to explain that the connectivity pattern between two regions, um, while we are getting correlation, that correlation is dynamic in nature and it changes as a function of time, right? Um, like what can we do with that information? And the third thing, which I'm like the original resting paper, state paper that I'm getting a lot of trouble publishing is looking at functional connectivity in the white matter. Okay, so the first is that, as I mentioned, um, this is the frequencies that is observed in electrophysiology, right? You have the delta waves, theta, beta, gamma, the like there is, fast and then ultra fast, right? However, with resting state, we only are using frequency up to zero point 0.1 hertz or a little higher than zero point 0.1, right? So most of the fMRI study have used 0.01 to 0.1 hertz, right? Because of the sampling. Now there has been different pulse sequence like multiband technique, and with multiband you can collect data at a much faster rate, right? So instead of one volume every 2 seconds, with multiband you can perhaps collect data every 600 or 700 milliseconds. So instead of one time point every 2 seconds, you can get 3 time points every 2 seconds, right? So one can look at the higher frequency. At least we would make a slightly, better improvement in this region. In electrophysiology, these between 0.0 and 0. Like this band, there are four frequency ranges, right? Slow 4, which is 15 to 40 second. Slow 3 is 5 to 15 seconds. Slow 2 is 2 to 5 seconds. And slow 1 is 0.7 to 2 seconds. So with multiband, we can look at all these frequency, right? So then like an obvious question is that, how is the resting state signal, right, distributed? I had told you that everything is below 0.1, but as we collect more data, can we subdivide that information? And would there be anything significant as we collect data at a faster rate, right? So here what we see is the slow 5, right, which is between 0.01 and 0.027, right? So this is FEF, frontal eye field. This is PCC. These are like two common areas where we have shown connectivity before. So we can see the connectivity then for slow 4, which is between 0.027 to 0.073. We can see connectivity pattern between 0.073 and 0.198. We can also see connectivity pattern. However, as we go beyond that, there is still connectivity pattern, but it is not as strong, right? And whether it is due to, you know, low signal to noise ratio, because there would be more noise in this range, or, you know, whether this represents some unique pattern, this remains to be seen, right? That's one issue. The other issue with this electrophysiological data is that if you look here, right, the range is between 0.01 to 0.027 here. So it was about 0.26 is the bandwidth, right? When you go to here, it is about 0.5. Here it is 0.12, right? So each band, the bandwidth doubles, right? So could that be a factor, right? So those things have to be seen, right? There are other ways to analyze it. One could simply, like, rather than using electrophysiology, if we have data till zero point 0.5 hertz, one could just do 0.01 to 0.1, 0.1 to 0.2, 0.2 to 0.3, 0.3 to 0.4. So that would be making the signal equidistant, and then one could also analyze this. Right. Uh, so this one is the high frequency, right? Yeah, that is the highest one, right? So I feel that this 3 is better because there is like similar correspondence between the 3. Here there seems to be slight reduction in the connectivity pattern, both for slow 2 as well as slow 1. Noise is the least. No, the noise is higher here, right? Yeah, the noise here is higher, right? Because these are the higher frequency signal. This is a study where by uh, Fashua Lin, and where they showed is that while traditional fMRI looks at this one, right, the green signal, and using moving average filter, you can see the low frequency fluctuation and the respiration signal. What they have done is collected data. Can anyone tell how frequently they collected data for this data set? So this is 5 hertz. So how fast did they collect the data? I think we had discussed this in the class, right? If my heart rate is 1 hertz, then I have to collect how many time points? 2, right? So for 5 hertz, how frequently do I need to collect data? Maybe Surya? Very good. So you have to collect every 100 millisecond. So this is how they collected the data, right? And what they showed is actually quite interesting is that, so this is during task. You can see that, so during task, there is a slight change in their respiration signal. Also, there is a slight change in the heart rate. And some of the EEG literature suggest that, during task, especially, fearful images and so on, it can cause a difference in like respiration or heart rate. So as if one could collect data at a much faster rate, then one would be able to not only look at cognitive changes or more like changes corresponding to the task, but one could also look at the underlying physiological changes if there is any significant change occurring, right? So again, example would be if you are to be given painful stimulus, right? So maybe when the stimulus is given, you would get a response in the corresponding brain region, but maybe the heart rate or respiration rate may change also because of, you know, anticipation or other physiological factors. Okay. And with this data, what they did was they looked at it at two bandwidth between 0.01 to zero point 0.1 and at between 0.5 to zero point 0.8 hertz, right? And this is a very interesting way to analyze because the stimulus that they gave was at this range, right? So in some way, by doing this, what you can basically do is assuming the task response and the low frequency fluctuations that we observe are independent, then we can look at the connectivity, the resting state connectivity pattern, as well as the task pattern during the same scan, right? And one could see, you know, does does the resting state pattern remain fixed or does it change with time with the, in any way is it related to the task activity, right? So that is, and then here what they have also done is looked at like initial condition and then used frame wise, like this is using like 30 seconds window, this is for the rest, this is corresponding to like to this frequency, and then showing how there is a difference, right? This is using a window length of 60 seconds, showing this, and this is 120 seconds, right? And what they are saying is that maybe there is more phase variation in the connectivity pattern compared to the task pattern. But depending on how the stimulus was designed, this could be affected. But again, this is another way to analyze not just the resting state data, but also the task data, right? You can, if you have 10 data points every second, right, then if your stimulus is even 3 seconds, then you can see how these signal responses are evolving with time more finely, right, compared to when the data is collected every 2 seconds. Right, right. Right. So in because again in this study, the way they have defined is that they have said the resting state is in the low frequency, right? That's what we have assumed. But the stimulus they have designed at a higher frequency, right? So the frequency at which the stimulation was done is at a higher frequency. So this is one way in which one it can be studied at two different frequency. This is again like using this is from another group. This is work by Vesa Kevenimi. Um, I had showed his work before. So here what they are doing is they are also collecting data at 100 millisecond sampling, right? And what they are saying is that this is the very low fluctuations, like these are the fluctuations from which we can generate the resting state network. But what they are also saying is that one can look, you know, the changes in the brain corresponding to the respiration. And this is showing the respiration, right? So the respiration, as I have mentioned, would be more sensitive to flow changes, right? So you can make a map which corresponds to the changes in respiration fluctuations and correlate on the whole brain and then show which regions are more active. Okay. Similarly, you can do for the cardiac, right? Currently, cardiac signal cannot be collected, right? Because we are collecting every 2 seconds while cardiac signal typically occurs 1 per second, right? So it would be aliased. By using this, we can also see how does the cardiac image look like. Okay. Right. So this is the resting state networks, right? So this is the low frequency between 0.01 to 0.1 hertz. Um, I should say there are some limitation of this method. Can anyone say what those limitation would be? Mm-hmm. Mm. So, um, okay, so maybe let's go back. Let's think back of the original image, right? The perhaps the first image I had shown in this course was like anatomical image takes maybe 3 minutes to collect, 1 millimeter by 1 millimeter. The functional image collect we take anatomical is 1 millimeter by 1 millimeter, functional is 3 millimeter by 3 millimeter, and it takes about 2 seconds to collect. So the way they can collect 100 data in 100 millisecond is by using 4 by 4. So the spatial resolution is more blurry, right? So that is one of the challenges. So you don't have the spatial resolution of a data which is 2 second uh, sampling rate, right? So the data is uh, looks more blurry, right? You cannot that easily find anatomical locations, but nonetheless these are fMRI data, and you could process them. Again, this is another this is like task activation. So they call it, so now they're calling this MREG, right? Like MREEG. So MREG, and this is CHE is cardiovascular hemodynamic envelope, right? And what they are saying is that for some of the studies that they did, this is how the average bold signal looks like. And then for the same region, right, when they look at the cardiac signal profile, it looks very similar to the task response. In fact, they are saying that the bold has a 1.3-second lag compared to the cardiac hemodynamic envelope. And so maybe that is how we can better, for different brain regions, we can have a very precise information about the delay, right? So now when someone does, let's say, finger tapping, right, the idea is there is a specific brain region called supplementary motor area which first lights up, and then the motor areas light up, right? Because the supplementary motor area tells that, okay, you have to do this. But that delay is maybe 300 millisecond or so. And by able to do these kind of studies, you could look at temporal delays between different brain regions. So this is for task. We could also do the same thing for resting state scan. Like this is an area which is rapidly evolving. The other assumption about these studies, I should say, is that in statistics, we make the assumption that the data points are independent of each other, right? That is how we compute the statistics. In this case, even when we collect data at 2 seconds, right, the data points are not independent of each other. There is some dependency, there is some autocorrelation. In this data set, I think I will keep it. So in this data set, that is certainly not the case, right? So there is a large temporal dependency, right? While in data set where the sampling rate is 2 seconds, maybe one data point would be dependent on the previous, or maybe one or two. In this case, it may be like 10 or 5, right? So there is more autocorrelation which is present in this case. And again, like for fMRI, especially for task activation, the assumption is that each data points are independent of each other, which is not the case. And especially in this case, that is not the case. Okay. The next thing I want to cover is modulation of functional connectivity, right? As several of you had mentioned yesterday and day before yesterday, like when we scan someone, there are so many factors, right? Maybe they are a little nervous, maybe they are thinking about food, maybe they're bored, maybe some may fall asleep and other things. And so as a subject lies within the MRI scanner during a resting state study, they may experience a variety of cognitive states along with changes in emotion and variable arousal levels, right? And accepting we don't know what will happen when, right? So we have no idea. And it happens that, when we look at correlation between different regions, there is functional connectivity. But to look at this variability, what has been done is called dynamic connectivity or slide. And the sliding window is the most commonly used approach, right? And one option is that you take one window of certain length, compute the correlation, then take the next window of the same length, compute the correlation, and then do it for the entire data set, right? So this is called segmented non-overlapping, right? So you can do that, and then you can find the values, and it will tell you how much variability there is in the data between two regions, right? The other option, maybe the more popular option, is that you take one region, then you have some overlap and go to the next one, keep the window the same, but shift it by a certain number of points, right? So if you had 500 time points, one option is you can keep the window length as 50, right? In one case, you start from 1 to 50, 51 to 100, 101 to 150, till you reach 500, right? So you would get uh, 10, right? 10 blocks or 10 measures of connectivity. The other one would be you start from 1 to 50, but then you can move it by 3 or even 1. Then it would be 1 to 51, 2 to 52, 3 to 53, all the way to 500. So in that case, how many windows would you get? Much more, right? You would get something like 450, right? Because you're shifting only by 1 point. So you can go all the way from 1 till 450 where it reaches the end, right? So when you plot 450, you can make like a nice looking plot like this one, right? And this is showing variation in functional connectivity between two regions, right? So to mention again, like if we were doing left and right motor cortex, we saw connectivity. In this case, the previous approach, you took 500 data points from the left motor cortex, 500 data point from the right motor cortex, you did correlation, you got one value, right? By using dynamic connectivity, using non-overlapping, you would get 20 correlation values, right? Because they are non-overlapping between left and right motor cortex. And by using overlapping, you would get 450 correlation values, right? So now that you have, let's say 450, you can also look at this profile. How do they look? Is it flat? Does it change a lot? So you can look at not just the mean and the variance, right? So what should be an ideal window length? Any guesses? Hmm? 3 or 4 data points. What would happen if you correlated left motor cortex 3 data points with right motor cortex 3 data points compared to 500? Hmm? Would it be negligible or would it be too noisy, right? So what would happen if you used 50? Is 50 okay, or should you use a different number? So no one really knows the answer, right? No one also knows what the steps. So this is called the window length, right? The length of the window. And this is called the step size. So both are variable. And many people use different window sizes. And there is no consensus in the literature as to what should be used, right? And you can anyone explain the reason why? What is the trade-off as you change the window size? What would be the trade-off? You are doing machine learning, you should be able to say. By changing the window length, like, so by changing the number of data points, what happens? You are introducing more noise or uncertainty, right? So that is the trade-off, right? So if I use only 30 data points, I'm introducing more uncertainty. But if I used, let's say, 100 data points, because each one is 100 data points, um, I'm, I don't have much temporal information, right? Because if we use this approach, I find something between 1 and 100, 101 and 200, right? So I only now have 5 measures for the whole data set, right? My estimates are better, but my number of observation is less. If I reduce to 50, my number of observation is 10. However, my estimations are noisier, right? Did I explain properly? How would you explain? How would you explain it in machine learning? Okay. Yeah. Hmm? Right. 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 Okay. There is no cons like non-overlapping, you mean? No, non-overlapping doesn't give you enough data points, right? It won't look like this. You will get like measures. And while I feel that this is a better approach because this is like redundant data, right? You only have, if your step size is 1, between first and the second one, you're only adding one bit of one data point, right? So they are highly redundant, but you get to make like figures where you can see like a continuous kind of thing. Yeah. Any other question? Right. So people have come up with many different approaches, and right, one is called cap analysis. The other one is called the QPP, like someone had mentioned in the class about, was it in the class? Like quasi-periodic, when you assume that the signal is not exactly periodic, but kind of. So then you describe it as quasi-periodic. And so with cap analysis, you take one data point and then you find images in the time series that would match, right? So it is done on one data point, and one can see how the profile is. In QPP, you look at the quasi-periodic structure of the data and then try to infer about how does this change as a function of time. Again, in both the cases, we are looking at the dynamic structure of the data. So, so another way that this is done is that, okay, this is between two time point, but you can do for every region with every other region, or even every voxel with every other voxel, and make a correlation matrix like this. And then for each time point, you can generate a series of correlation matrices, right? So from the matrices, you can then say that, okay, this is my 5 regions and these are the values, and then you set the threshold, and then you binarize them, right? And once you binarize them, you can, one approach is to plot them in this fashion, where it's a binary image, so it's either connected or not connected. This one is they are connected, but it also represent the strength. You know, if between C and B it is 5, right? C and B, it will be a thick line, right? Between B and D, it is connected, so it is also a thick line, right? If the connection is low, let's say between B and E, okay, it should be a thin line, okay? So the correlation values would represent, and this is just showing. I should say that this approach is used in fMRI, but we have to make slight change, right? Can anyone tell what that change has to be? I will give you a hint. The range of correlation value is between -1 and +1, right? Based on that information, will we be able to use these approaches that I just showed? Anyone? What do you mean? Mhm. Well, the first problem is that in here, right, in typical graph theory, um, it is all positive number, right? -1 still has functional meaning, right? But in graph theory, we don't know what to do with -1. So one approach people have used is to take only absolute values. That is one approach that, okay, you know, whether it's plus 0.9 or minus 0.9, they both are equally significant and we should take them as 0.9. The other approach which some people have used is that they ignore the negative value and only take the positive value. So, but now more and more people are taking the absolute value, right? Again, if someone could find a way, because when you take the absolute value, it also has challenges, right? Because 0.9 and minus 0.9 are different. They convey very different, perhaps very important information, right? And how to take that into account and process, like if anyone can find out, would be really, really good. So then what is done is from these measures, one can find a number of graph theoretical measures like centrality, node strength, local efficiency, clustering coefficient, small worldness, right? And this is just like an example, right? So this is like a regular network, right? So in this case, the clustering coefficient is very high in a sense that you can connect from any point to any other point, right? In this case. But the average short path length is also very high, right? It would be, if we give the airport example, can someone explain to me what this one would be? How would we explain this one versus this one versus this one? So let's say these are different cities in India, right? So what it means is that there would be, let's say, one flight from Allahabad to Banaras. There can be multiple flights, but to go to, let's say, um, if this is Allahabad to Banaras and this is Banaras to Delhi, the only way you can come to Banaras is either through Delhi or through Allahabad. No other way, right? It is not very efficient, right? Although you can go to from one point to any other point, like, but there is very little cross connection between them, right? And the problem with this is, let's say, um, for some reason, the Banaras airport was closed down, right? Then you cannot go if you are, um, you know, either here and you want to go that side, or from here if you want to go to this side. This one is called a small world network. And the idea here is, can anyone explain? So, so these are, you can think of as a hub, right? So there are a few hubs, right? Maybe this one is Delhi, and maybe this one is Bombay, right? So then what we are doing is, it's like you can still go from one point to the other point, but even if one is closed down, then you can go through the other ways, right? So this is called small world network. And this one is called random network, that, you know, there are many other connections. And typically, you know, this is very expensive, right? Because like there are so many, you know, you have to have so many connection between different locations, right? So this one is something which is more commonly used, right? Either through for airports, or also through, the other example would be your communication network, like, or internet network, like there is Google, Amazon, and a few others, which are the major hubs, right? So any, like, those are the ones you go through. So as long as they are resilient, you can go to other sites without much trouble, right? So similarly, um, brain has been shown, again, this is a whole topic in itself, so I'm just very briefly covering, but I can, if someone is interested to know more, I can um, cover later. So also, because like tomorrow I'm going to cover different, like, controversies and areas, if there is some topic that you would like to be covered, please let me know, then I can add those tonight. Okay. So with graph theory, what you can do is, this is time varying functional connectivity, right? So you can use this window to make like this, and then you can do whole brain connectivity, and from that we can find different connectivity pattern. Also, we can look at from this, we can, using k-means clustering, we can find different states, right? As I mentioned about, like in EEG, there is microstates. By doing this, what has been shown is that there are about 7 states, right? Sometimes the interpretation of that is a little difficult because we are looking at correlation matrices. But the idea is that when you take healthy subjects, you get like 7 different states, and you can analyze disease states and find differences between these networks, right? Again, so the other way we can do is we do group ICA to find, let's say, different network. Then for each of these networks, we do window-based correlation, right? Then we do like time frequency analysis. And then from that, we can look at the profile, right? And from that, we can generate maps like this, right? From which we can say, this is connected to this, while in this case, they are connected like this, right? Again, in this case, we don't have to make the assumption that which we make in ICA that each network is independent of the other one, right? Here we are looking at the graph theoretical approaches and looking at different regions and saying that, okay, this region and this region are connected. And this is how the dynamic connectivity pattern is, right? And again, we have like these correlation matrices. DFC is dynamic functional connectivity. Some call it dynamic, some call it time varying, but it means the same. And then you can generate how the connections are for different brain state, right? For different brain regions, the connection is like this. For state 1, for state 5, the connection is this. And this is how the correlation look like. And then what you can do is you can show between, let's say, healthy control versus schizophrenia. This is work by Vince Calhoun, who has shown that by using these kind of analysis, you can show differences in healthy control versus schizophrenia. And so red is where healthy control connection is greater than schizophrenia, yellow where healthy control is lesser than schizophrenia, and so on. So you can make these like profile, right? So what we were interested, so I think just this is restating what I covered. So what we were interested is that when you have two regions which are connected, could it be that there is something unique between them? Or could it be that there is a third region which is influencing the connectivity? So if there is dynamic connectivity between these two, could it be that something which is between this, or could it be that there is a third region which is influencing the connectivity profile, right? So whether they have some functional significance. So the question we ask is, are modulatory interaction present in resting state? That can one region affect the connection between other two regions? Second is, like, is there any modularity interaction between default mode and task positive network? And finally, whether modulatory interactions are modulated by task demand, right? So in this case, we used default mode network as our third region, right? So our hypothesis that default mode is affecting the correlation between PCC and MPFC, right? So that is the region where Katie Chang first showed that there is dynamic connectivity. And they had labeled them as task positive, task negative, and so on. I feel that maybe one can be not so stringent about the definition, and that based on the task or based on the brain region, we can see which regions are getting influenced. Um, did I answer your question? Yeah. So the next we wanted to see is that while that one was for um, a region between within the default mode, here we are looking at um, across different networks, right? Like which regions are influenced when salience network and default mode network have connections, right? And this shows a fairly large region that salience network influences the connection between the default mode and the task positive network. And then this is a very simple task of eyes open versus eyes closed. And by doing this kind of analysis, what we show is that the left thalamus, right, versus the left calcarine sulcus, those are the regions which are involved in eyes open versus eyes closed. That is the only difference we see. That is why when you had asked like whether one should do eyes open or eyes closed, in my opinion, it doesn't matter that much. There are other issues, but within brain, it's okay. So then by quantifying this, if we were to quantify, um, what we show is that this is the somatomotor network, right? Default mode. So what we did was we used two data sets, the Human Connectome project and the UCLA data. Uh, I'm going to upload all the slides, so you don't have to. Okay. So we used the data from the Human Connectome project and the UCLA data, and we investigated 7 tasks, right? And we performed whole brain analysis, right? So this is like the definition of functional connectivity. There is a fixed, right? And then there is beta 1 x plus error. Like this is the definition for GLM. For regression model with multiple condition, you have beta 0. This is the physiological interaction. This is the psychological interaction, right? And what we are trying to do is study this, that could it be that there is this interaction that we are not capturing with task activation. And these are the different tasks that we used, right? Emotional task, gambling task, language task, relational task, social cognition, working memory, and then stop signal task, right? So all this is from the Human Connectome project, but because Human Connectome project did not have like a event related task, we used the UCLA data, right, which was a stop signal task. And so what we get is the responses for different tasks using GLM, right? Just to see how they look. This is next one. We show something like this for the language task. The red shows activated region and blue shows deactivated or like negative region, like it has a negative connectivity. Okay. And what we find for each of these tasks is that the number of associated region seems to be very large and not like a small activation region. And when we plot them, right, this is for the social cognition task. This is increased connectivity, like increased hubs, activated, non-activated, deactivated, right? So there's a lot of activity, both positive and negative, right? And we can display them in this fashion also. Again, like for language tasks, there is a lot of connectivity for social cognition task, working memory, stop signal task, and we can display in many different ways. Again, the point is that there is widespread connectivity changes, both increased and decreased connectivity. And the relationship between task modulated and regional activation is not so clear. Also, co-activation does not necessarily imply increased connectivity. Also, reduced connectivity may play an important role in task, right? So one of the uh, maybe another way to describe is that there is always this question that, you know, when you perform a task, there is an increase in blood flow, and specific regions get activated. But that increase in blood flow that happens, is it, are there other areas which are getting compensated, right? Are other areas where the blood flow is slightly reduced because it has to supply more, right? And again, I don't think we can clearly answer that question, but at least it suggests that the task response is more complex than what we get using, correlation analysis or t-test, right? Maybe they are the first initial way to analyze the data. One drawback of the study is that we need a lot of data, right? For us to get these results, we had to use like 100 subject from the human connectome, which is very high quality data. I haven't shown, but we also have analyzed data from schizophrenia, like because UCLA data had schizophrenic, and we see differences in these connectivity pattern between healthy control and schizophrenia, suggesting that there is something functional information that can be gained by using these kind of analysis. Any question? Right, right. Yeah, yeah. And again, I think I can give you examples, right? Like maybe you can think of better examples where um, if you had, what would be an example? Let's say if I'm driving in a snowy road, I don't want to talk to anyone. Like if someone calls me, I won't pick up the phone because I want full attention, right? And maybe talking would um, like reduce. But if I'm driving on a highway without much traffic, then not a problem, right? One would be bored and perhaps one would like to talk to someone, right? So the challenge is like to understand, like for different tasks, you know, um, how are they getting, how are the connections getting affected? If maybe those of you who have psychological background can think of a task where you could change, right, would be very interesting way to um, analyze the data. All right. Any other question? Yeah. Right. 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 I haven't looked at it, but we can certainly look. We can find out, like looking here. Um, so maybe the last topic I want to cover is white matter connectivity. So I had told you like how my initial papers got rejected. So I'm facing the same trouble again now on this topic, right? And so far what we have covered, right, in fMRI as well as in resting state, what we have assumed is that all the signal is from the gray matter, right? From the first day, that's what I said. Like in the gray matter has good vasculature, there is good blood flow, there is neuronal activity, and when you perform a task, there is an increase in signal intensity. Um, uh, However, the brain, right, about 50% of the brain is white matter, and the other 50 is gray matter, right? And in certain cases, um, like with age, right, with every decade of life, it is the gray matter which deteriorates first. Um, and the idea is that should we be ignoring the white matter, right? So there is a whole literature as to what to remove, what is a noise source in fMRI. And a very common approach has been to use the CSF, average CSF signal, the in addition to the motion parameter, the average CSF signal and the white matter signal as signal of no interest, to basically suppress whatever you get in like white matter, right? However, there is a literature um, by Judy Gorlick where they showed that for some studies, for some activation study um, called the Sperry test, you get activation in the corpus callosum, which is in the white matter. And there is another test called Poffenberger, where also you see activation in the corpus callosum, which is the white matter. Right, they do see some activation in the gray matter, but there is activation in the consistent activation in the white matter. There was another study by John Gore, a very famous physicist, where what they did was they did diffusion and then they changed the task load, right? One was a little easy, the other one was harder. And what they found was as the task load increased, the white matter, the activation or not active, the white matter tracks, there was more signal there, right? And another paper by Michael Peer showed that you could do clustering to look at these changes. So what we did was, we took data from the Human Connectome project and focused on the white matter, focused on the corpus callosum, which is the largest white matter track, right? And we took, basically the way we did was we took every voxel from the corpus callosum, correlated with every voxel in the white matter in the brain, and then did a k-means clustering, right? And when we did the k-means clustering, what we found was that we could identify a left prefrontal white matter functional network, and that this correlated to this region of the corpus callosum. Similarly, we could identify a tempofrontal white matter functional network, which showed up here, right? And similarly, a number of other networks, right? So first, we could find white matter networks in the brain. Secondly, these happen to correlate to specific part of the corpus callosum. Because we were using Human Connectome data, they have another scan, right? They have they have actually 4 resting state scan, but we used another resting state scan which was collected on a separate day and then reanalyzed the data in an identical fashion. And what we found was that during the second run, this region correlated with this. So the spatial overlap was good, right? I would say like very good, like yellow, green, purple. They match quite well, right? Again, this would suggest, again, this is using about 200 subject across 2 different days. And the fact that we are seeing such good correspondence suggests that, these networks are real, and then we can use to identify different networks in the white matter, right? So this paper got rejected 5 times. so, so because we have DTI for the Human Connectome project, we could do the DTI, right? The corpus callosum has been very well characterized using DTI. And then we saw how does, like, we matched with the previous figure, which, right, from this figure, we matched like this network with the first DTI network, this one for the second one, the third, and so on, right? And what this shows is the overlap between the DTI and the functional connectivity map. Okay, so the red is the overlap in the functional connectivity, resting state functional connectivity and DTI. So in this case, not all the DTI tracks overlap exactly with the functional connectivity map, but for many of them, they overlap quite significantly. And I still don't know whether the difference is due to some noise issue or partial voluming or limitation of the DTI tracks the way it has been done, right? To further investigate, we wanted to look at the noise structure within the white matter, right? So this is the brain white matter network. This is the random network. And again, suggesting that these parameters, the fact that they are different suggests that the noise property is not due to random noise. This is a study by Huang, not our study, but where they showed they had very high spectroscopic EEG signal, the intracranial electrophysiological signal, and they looked at the white matter time series and then correlated with the stereoscopic EEG signal and showed that between 2 regions, the correlation was fairly good, right? And again, suggesting that maybe even the electrophysiological signal that they obtained has something to do with the, or can be modulated, or I should say, reflects the white matter signal. And so this is looking at the bold functional connectivity, and this is stereoscopic EEG functional connectivity. And again, like one is like it's not simultaneous and done differently, but nonetheless the correlation is significant, right? Does anyone have any questions? I'm going to talk about Alzheimer's later today. So this is just showing homotopic differences between normal control, like mild MCI and MCI, and showing some of the differences in the white matter. And again, this is in the middle occipital white matter region. showing that this is healthy control MCI and very mild MCI to show that there is a difference in this pattern and that it can be used. This one is using clustering coefficient for different regions with gray matter, also using white matter. And again, the point is not to say that you should not use gray matter, but the point is to say that you should use gray matter because that's where most of the signal is, but also use the white matter because you're getting this signal for free. It's additional analysis, but by analyzing perhaps with machine learning and other method, you could improve your accuracy by combining everything. Also, I have like a very good student called Pratik. So he has developed this toolbox called YFun. It was released, I think, this year. And so it does like pre-processing, it does gray matter functional network creation, and then Atlas, as well as region of interest based analysis. It can also do statistical testing of functional connectivity, right? So this is the processing pipeline that is used, like fMRI data, anatomical data. It will do the segmentation, co-registration. It will identify CSF voxels from anatomical image and extract CSF signal from resting state signal, right? And we can do the regression. This is the motion parameter. If you want filtering, it will do it. And then it will take all the participants, like it will create white matter mask, gray matter mask, and then it will create gray matter functional network as well as white matter functional network. Like this is like the corpus callosum, how they are related to different regions, right? So it can also do, once you identify the regions of interest, it can also do correlation analysis, right? And then once you have the different correlation analysis, you can do different statistics with different parameters of interest, and then you can use test for multiple comparison. And this one is like completely menu driven, and you just need to click and then you can analyze the data. I didn't want to you guys to use it because I feel it would be awkward to promote something we have written. So, but I really think that you should know a little, like the different things that you're doing in analysis method. And once you do it, then maybe running it by script is okay. But I feel that, actually, I strongly feel that you should know at least the steps and what it does, because I feel that maybe for the next analysis, based on the problem you face, only you can come up is like what is the best analysis to use, or what is the shortcoming of existing analysis method. And it can also create publication ready figures. So if you have any question, I'll try to answer. Yeah, so this one is MATLAB driven. However, we also have a Python based version. The way it works is that Pratik is writing all the codes in MATLAB, and there is a student from computer science who is writing making these like the interface look just like this using Python and having all the scripts in Python. We would like to make everything in Python because it's, like so that you don't have to buy MATLAB and run. The challenge is that MATLAB is so easy to use, and there are many functions which have been optimized and work very well, right? And again, um, like I'm new to Python, and the student who is in computer science, um, he's good in Python, but for he's not very good in scientific programming. So it's we are all learning. If anyone wants to contribute, let me know. It's like it's all in GitHub, right? So if you want, um, we will be very happy if you also give feedback, even for the MATLAB one. If you can crash it, I will buy you chocolate. You know. Okay, I'll try to answer any question you have. Yeah. Oh yeah, yeah. So it was a neuroimage. Uh, yeah, 2020. Yeah, so I should have maybe, I thought I would, um, I'm underestimating, or I'm overestimating my time. But we have used this for couple of disorders like schizophrenia and epilepsy, in addition to white matter. So there are others who have used it um, for, um, let me think, like schizophrenia, epilepsy, um, Alzheimer's. Um, we are trying to work on multiple sclerosis because multiple sclerosis has white matter lesion, um, and then aging also. Uh, mm, I can show you. Let me just see. I can show you later. There is so with so what we are trying. I can tell you. So what we are trying to do is look at the developmental like so from um, the age range we are using is from 18 to 80, very similar to yours. So what we want to know is that, like with aging, the gradient, the gray matter networks become weaker, right? But the gray matter volume also goes down, right? By 0.1 with every decade of life. But the white matter is not as, it doesn't like deteriorate as fast. So what we want to know is that what is happening to the white matter functional network? Are they more resilient than the gray matter? And if that is the case, can we use it in some way to predict the age of the person by using both gray and white? Um, I think that is, yeah, that is what we are trying. We are also looking at like development from like infant to like 12 or 13 years of age. I had mentioned like there is this ABCD data, adolescent brain uh, child development. Oh, so so in that, um, like 10,000 subjects are being scanned um, across 10 years. So from the same data, we can get uh, longitudinal as well as cross-sectional data, and then to see what is the developmental projectile. Any other question? Okay. If you want, I can cover some work I've been doing on drug abuse, but it is up to you. Maybe I should just stop, right? Okay, no problem. Maybe tomorrow I can cover some. How